Hey, I'm Austin, and this is my video report for Physics 2211, Lab 3. Now, this lab was divided into two parts, and the purpose of the first one was to use a computational model to predict and analyze the motion of a star in orbit around a black hole, then use that data to determine the mass of the black hole. The purpose of part two was to use another model to determine which initial velocity is necessary to pass close enough to the black hole without crashing after taking off of a planet also orbiting around the black hole. As you can see here is a little preview of my results. My mass of the black hole I found was 8.01 times 10 to the 33 kilograms, and these are my force components. Now for some of the main physical principles used in this lab, the gravitational force formula, which is the gravitational constant times the masses of both objects divided by the distance between them. And right here, I just solved for the mass of the black hole to make it easier when I used it in the model. And I just used this formula right here. And this equation comes from Newton's second law, which essentially says that you can split the net force into two components. One is parallel to the direction of motion, and one is perpendicular. And here are the formulas for each of those components. And also from Newton's second law are the position and velocity update formulas, which I didn't put here, but they're also very important for this lab. Now for the model, or I guess the experiment details for part one, the system we're studying is the star. The surroundings are the black hole and the space around the star. The initial conditions were for the position of the star. It's randomly generated based on my email address, and the rest of the conditions were given. I'll show in the code in a second. For part two, the system is the spaceship. The surroundings are the black hole, the star, and a planet, which all exert a gravitational force on the spaceship. And then again, just the space around it. The initial conditions for part two are either given, I'll show in the code in a second again, or they were determined in part one, which was the mass of the black hole. And the velocity is what we're determining in the lab. Here are the initial conditions for the part one model. Obviously, the gravitational constant is 6.7 times 10 to the negative 11th. The mass of the star is 2 times 10 to the 30th kilograms. And then delta T is supposed to be 1 day, and there are 86,400 seconds in a day. So that's what I defined for this. Here's the rest of the model for part one. Here it just uses the definition of momentum, which is mass times velocity, to find the initial and final for both of those. And then delta V and delta P are obviously just the final minus initial. Down here it uses the fact that Newton's second law says that F net is equal to dp dt, which is the change in momentum over change in time. And here it just uses the formula for the parallel component of dp dt that I showed earlier to find that component. And then again, it just uses the fact that dp dt and its components are equal to F net and its components. And then here I just used the gravitational force formula and the rearranged form of it that I showed earlier to calculate the mass of the black hole. And I used a little counter in the loop to automatically calculate the average of the masses for that. And it's shown here, it's 8.01 times 10 to the 33 kilograms. And then right here is just a picture of the model after it's done running. Now for the model for part two initial conditions, I just plugged in the mass that I got for the black hole from part one, and the masses and constants for the rest of the objects are given here. Now here's the model for part two. Here it calculates the position vectors between the planet and the other two objects, and then it uses those vectors to calculate the gravitational forces by those objects on the planet, and it adds up those forces to find the net force on the planet. And it does it all again for the spaceship down here. Now, next it uses the velocity and position update formulas to predict the motion of those objects. And as you can see here, here's the orbit of the planet, here's the motion of the spaceship near the black hole. And to find the initial velocities, I just used some trial and error and I just used what worked to get the spaceship as close as I could to the black hole. Potential sources of error in this lab for part one, I could have gotten the ship closer to the black hole before it shot off out of the system, only because I used trial and error to find a rough value for the velocity instead of actual calculations. The black hole mass could be inaccurate because it was found by just taking the average of all the calculated values, and the real one could have been any of the values, not just the average. For part two, if the black hole mass was inaccurate, then so would everything in part two, because everything in there depends on that mass being correct. And finally, the discussion questions. As for the rate of change of momentum versus the net force, the values and components are the same numerically, but they differ in the way that they're calculated. The net force requires inherent properties of the objects like mass to calculate, but the change in momentum is found by observing and comparing an object's position and momentum over time. And for the question about the ship moving into orbit around the black hole, I used some trial and error for this too, and I found that with this initial velocity, the ship will start to orbit around the black hole just like the planet, and it does cross the path with the planet at 2 points right here and right here, but otherwise their orbits are separate. So it could crash eventually, but it's not very likely for a long time. And that's pretty much it. So thank you for watching.